6.6, financial applications of recurrence relations, arithmetic. Now, 6.6 is broken up into arithmetic and geometric because we are discussing 4 different concepts. It was easier to break it up a little bit so that you're not confusing yourselves with things like flat rate depreciation and reducing balance at the same time, and then simple interest and compound interest. So our learning intention for arithmetic is what is depreciation and simple interest. As success criteria, I can define depreciation and simple interest. I can find depreciation and calculate future values using recurrence relation. So flat rate depreciation recurrence relations. Flat rate depreciation calculates the future value of an asset by reducing the value every year by a fixed amount. The amount can be given in dollars or as a fixed percentage of the purchase price. The future value can be written as a recurrence relation. Okay, break it up a little bit or explain what depreciation means. Depreciation is used to describe the decrease in a value. For example, you buy a car for $10,000. It loses, its life is, about 10 years for a car. It loses $1,000 per year in its value. So after a year, it's only worth $9,000. That $1,000 is called, or losing that value of $1,000 is called depreciation. And not just talking a car, we're talking computers, equipment, machinery, things like that. And the future value, for example, if we said it loses $1,000 every year, after 3 years, it's lost $3,000. So the future value is called the value of it in 3 years is called the future value. I'm getting my words confused. We've got our initial value or our purchase price of our asset. Then we've got the dollar value that it loses each year. So the recurrence relation for flat rate depreciation after n years, we talk about our n value again, can be modelled by the arithmetic sequence recurrence relation V of O equals A, V of n plus 1 equals V of n minus D. All right, I'm going to take a step back. Let's go back to 6.1. In 6.1, we learned T of 1 equals A. So if we're talking a negative D value in this case, T of n plus 1 equals A minus D. Oh, hang on a minute. No, that was T of n minus D. Here we go. For any n value. In finance or financial maths, i.e. 6.6, where you're going to use V of 0. So 0 is our initial n value. And we're using V instead of T's. N plus 1, V of n minus D. Now, apart from changing the pronumeral or the letter and starting one step before at V of 0 instead of V of 1, is there any difference? Not at all. It's a very, very similar concept to 6.1. So, V of n is the future value of the asset after n years. A is the purchase price and D is the dollar depreciation per year. Now our D value is always going to be a negative. Let me just highlight that there. Why? Because it's losing value. Go through a worked example. If you are following in the textbook, it is page 286. So, a ride-on mower is purchased by a gardening business for $9,500. Its value depreciates at a flat rate of 5% per annum. Now, remember, all we needed in arithmetic sequences was our A value and our D value, and we could find any year or any nth term from those two figures or from those two values. This is no different. So a ride-on mower is purchased by a gardening business for $9,500. So that is my A value, so my purchase price or my initial value. It value depreciates at a flat rate of 5% per annum. Now, I don't have a dollar value, I have a percentage. that means I need to find, i.e. part A, the annual depreciation amount. So I need my 5%. I'm going to carry this one up here because I've got a bit more room. 5% is 0.05 when we're talking decimals. So we want to find what 5% of 9,500 is. Put it in my calculator before and I got $475. So that is my D value. Write a recurrence relation for the future value of the ride-on mower. What shape will the graph be? Now we're talking arithmetic, so we know it's going to be a straight line. And we know that it loses value, so we know our D is negative. Where are we? Recurrence relation V of 0 equals A equals V of n plus 1 equals V of n take D. Which, when I substitute values in, is V of 0 equals 9,500, my initial amount. N plus V of n plus 1 equals V of n take D. Oops, didn't put a dollar value in. 475. Now, what shape will the graph be? We know, let me just make that pretty. D equals negative 475, or D equals 475. And we know that in arithmetic sequences, if D is positive, it goes that way. If D is negative, it looks like, oops, wrong screen, it looks like that. So in this case, we're following that red line and going downwards. Use recursive computation on your CAS calculator to find the future value mower after 5 years. So if you followed my CAS instructions from the other video, you would put in your 9,500, then you would press enter. Then you would put in subtract 475, enter, and that would give you your second value. Then you keep hitting enter until you get to after your 5th year. Remembering that we're starting at term 0, so you need to actually subtract $475 5 times. All right, so let's do this manually. So V of O equals 9,500. We knew that. V of 1 equals V of O minus D, which is 9,500 minus 475 gives me 9,025. V of 2 equals V of 1 minus D, and I use my previous figure, 9,025, take 475, equals 8,550. So all I'm doing is taking the previous term, or there, and popping it in as my new V of n value. I'll keep going through all the V values. So V of 3 equals V of 2, take D, which is 8,550 minus 475 equals 8,075. V of 4 is V of 3 minus D, which is 8,075 minus, silly hands, 475 gives you 7,600, and V of 5 equals V of 4 minus D, which is 7,600 minus 475 gives you 7,125. So the future value, I'm going to change colours so I can make it a little more obvious. Future value of the mower after 5 years is $7,125. So we had to do this 5 times and do it step by step, as in using the previous year's value to find our future value. All right. Simple interest. So we can go down in value with depreciation, but we can also invest money and start to accumulate interest and have our value go up. It's not all negative. So simple interest recurrence relations. A simple interest investment is an investment where interest is calculated for an agreed period and paid only on the original amount invested. The recurrence relation for a simple interest investment is similar to the recurrence relation for flat rate depreciation. The difference is we are adding rather than deducting a fixed amount in each time period. So really, the only difference is instead of having a negative D, you've got a positive D. So the recurrence relation for a simple interest investment after n years can be modelled by the arithmetic sequence recurrence relation. V of O equals A, V of n plus 1 equals V of n plus D. Okay, so if you got that previously, you would see that the only difference is I now increase my D value. I've still got my V of n equals my V of O equaling A, my V of n plus 1 equaling V of n. Then I add because I'm increasing my value. So V of n is the amount in the account at the end of the nth year. So for example, you have $200 and it increases by $10 each year. At the end of the first year, you've got $210. So that then becomes our new V of n value. At the end of the second year, you add another $10. It goes up to $220 and you use that figure for the subsequent V of n value. But we'll go through that in the example. A is the original investment event. It's one of those days I can't even talk. A is the original investment amount and D is the dollar interest amount earned per year. Worked example 14, if you're following in the textbook, is on page 289. All right. So Sasha invests $400 in an account earning 5% per annum simple interest. So A, write a recurrence relation for this investment after n years. What shape will the graph be? So we need to find our A value and our D value as a percentage. We've got those, but we need to find a dollar figure for our D value. So I know that my D value, we're not talking depreciation, I'm getting confused. My D value is equal to $4,000 times 5%, which is 4,000 by 0.05, which in this case is $200. So my D value is $200. Part A says, write a recurrence relation for this investment after n years. So V of O equals A, V of n plus 1 equals V of n plus D. Let's substitute. V of O equals 4,000, my initial amount. V of n plus 1 equals V of n plus $200. So what this means is every year your investment is going to increase by $200. So this recurrence relation has a positive D value, as I showed you in the previous slide. So it's going to look like a linear graph with a positive slope because our D value is positive. Use recursive computation on your CAS calculator to find the amount of her investment. Find the amount her investment will grow after 5 years. So we can do it the same way we did the previous one. I'll draw a line down here and try and split this up. So we've got V of 1 equals V of O plus D. 4,000 plus 200, 4,200. V of 2 equals 4,200 plus another 200, gives me 4,400. V of 3 equals 4,400 plus 200 equals 4,600. V of 4 equals 4,600 plus 200 gives me 4,800. V of 5 is 4,800 plus 200, giving me $5,000. So the value of my investment after 5 years will be worth $5,000. So that's part B. I'm going to pop a part B on the side here. That's A, that's B, both for number 1. Now, calculate the annual amount of interest earned. Hang a minute, has it jumped to another question? That's silly. Disregard all of this. It's just pretty much the same thing. It has just shown me, I didn't even realise what I've typed, I've just duplicated. So what I've actually done is I've shown you the steps on what to do. Calculate the annual amount of interest earned, write the recurrence relation, use recursive computation on your CAS to find V of 5. All right. An example question. Which situation is modelled by the recurrence relation V of O equals 23,000, V of N plus 1 equals V of N minus $1,200? So, our options are: a car originally purchased for $23,000 is depreciated by a reducing balance rate of $1,200 each year. A car originally purchased for $23,000 is depreciated at a flat rate of 12% per year. A car originally purchased for $23,000 is depreciated at a flat rate of $1,200 each year. A car originally purchased for $23,000 has been depreciated to $1,200, and a car originally purchased for $21,800 is depreciated at a flat rate of $1,200 each year. Now, I'm going to cross out this E, because my initial value is $23,000. That leaves me with 4. Now, next step is I've got minus $1,200. So that means it goes down by $1,200. So let's get rid of B. And because it's at a flat rate, I know I can get rid of A, which eliminates the reducing balance. I'm down to C and D. So it's depreciated at a flat rate of $1,200 or has been depreciated to $1,200. Now, because we're talking depreciated at a flat rate, that's going to be my answer. All right, my next video will be 6.6, geometric.